Okay, welcome everybody. And I'm going to do a couple of quick demos before we go back into more algorithms. So, yesterday we were talking about different variations of path search. So, we talked about that you can use Dijkstra's algorithm not just to find the travel time to one destination, but the travel time to many destinations. And that's really useful for pre computing optimal travel times that you can look up quickly as you're reordering things. That's kind of hard to visualize, but we also talked about you can get even a little more clever. And for the case where you're trying to find the shortest travel time from any depot to the various delivery intersections that are interesting, that you can actually use something called multi-source Dijkstra, which means you start not from one spot but from multiple intersections and look for the shortest path from any of them to a whole bunch of target intersections, which would be the delivery intersections. You can gain a little bit more speed by doing that. So let me just show you what that algorithm actually looks like. So this is multi-destination Dijkstra, and let's see. Let's actually, I want to go. Let me change this. I want to do a multi-source because let's say I've got three depots like that, and I now want to go find the path to some delivery intersection that's in the middle here. Let's see. Let me stop entering this actually, and I want to run the algorithm. So let's go click that. Hopefully you can see that. Basic idea is with multi-destination Dijkstra. Let me get rid of the depth first. I don't want that. I want Dijkstra's algorithm. Sorry, with multi-source Dijkstra, you can actually see that it's expanding from multiple places. So let's try that again. I'm going to enter multiple depots. Those are all my start locations. And now I want to find what's my shortest travel time from any depot to where my mouse is. So if I do that, you can actually see the wave search basically starts at multiple places. So you just put multiple start intersections into your priority queue, and you start the normal Dijkstra search, and it'll actually return this is the shortest path from any of these depots to this particular delivery intersection. It happens to be this depot is the fastest, and this is the path. So it's another small code change that you can use to reduce the number of path searches you do if you want to do that pre-computation, as we talked about yesterday. Let me visualize the traveling salesman problem now. So let's say let's see, this is actually not clearing. So let's just zoom out, zoom in. All right. Well, let me enter some depots here. Okay. So these are my uh, starting positions where my traveling salesman problem could start. And now I'm entering some delivery locations. So pickup and drop off, another pickup and drop off. So all the green arrows are pickups, all the red arrows are drop offs that go with them. So I'm basically just graphically entering a problem here. A whole bunch of deliveries that go all over the place, and I entered a bunch of depots that I could start at. Okay, and now I'm going to hit this salesman solve. So I basically just entered a traveling courier problem or traveling salesman problem, and now I'm going to solve it. Uh, in milestone 4, you're given 50 seconds to solve it. I changed our solution to only take 10 seconds, so I don't have to wait as long. Okay, and there's the solution that it came up with. So it said it should start at this depot up here, go pick this up, go pick that up, drop off one thing, pick up another one, drop off, pick up, and so on. So it followed this path around and eventually actually went back to the same depot. And this travel path looks pretty good. There's not a lot of backtracking. It looks pretty short given how many places we're going. So you don't have to make any graphics for milestone 4. Your TA is not going to see them or grade them. If you want to do that because it helps you debug or optimize, you can. It's not very hard to draw the output of your algorithm. Uh, and it might give you some nice visuals that you could show in your final presentation. Let's see. I'm just reading in the chat. Yeah, I think I'll have to read Isidore's comment afterwards and think about it more because that maybe take me a while to answer. So Okay, so let me close that down and let's go back to the slides and start going through a few more algorithms. Okay, so we're talking about iterative algorithms. And the idea of an iterative algorithm is greedy algorithms where you're trying to make a decision and construct a solution kind of one step at a time. At a certain point, they can get very complicated if you're trying to look too far into the future about, well, if I make this decision, what'll happen 6 decisions down the road. So iterative algorithms basically work in a different way. They say, give me a complete solution. And if you have a complete solution for, a big traveling salesman problem, so you've got many intersections you have to go through, then most of the solution is probably pretty good. But there might be areas where you can fine tune it. And that's the idea of an iterative algorithm. Give me something and I'll just keep making changes trying to make it better. And it's often easier to get a good solution by changing something that's completed than trying to rebuild something from scratch that's even better. Okay? Now we talked about for an iterative algorithm, it's useful to have a compact solution representation so that we can change it quickly because that's going to let us look at more perturbations. If we can look at more changes, we likely can find more useful changes and get a better final solution. So just to recap what we talked about at the end of last lecture, you can store the solution at all times as essentially a complete solution, a full travel path, but it's kind of a pain to work with if you're going to be doing a lot of local changes to your solution. So a better way to do that would be to just store in some data structure. We said you could use a vector where you store essentially an integer and probably like you could have a structure that is basically an integer intersection and a basically an enumerated variable, which could be one of pickup, drop off, and that would be enough for you to be able to tell in code, this is the first pickup, this is the first drop off, this is pickup number 1, this is pickup number 3, etc. So if I made a struct that had these two entries in it, and I made a vector of that struct, that allows me to represent my solution. And we talked about we could put the depots in there as well, but we don't actually have to. We can just choose our order of deliveries. And then once when we're evaluating the travel time of a given order, we know that we should always use whatever depot at the start gives us the smallest travel time to the first pickup or drop off. And at the end, we should always go to the depot that has the smallest travel time. So that actually means we don't need to represent the depots in this solution. We do need a function that can turn this solution representation into a travel time. And that function needs to look up what depots should I use. For that function to be fast, it should either use geometric distance, if you want to keep the function simple to estimate travel time, or to get a bit better result, more accurate, you could have it look up path delays that you've pre-computed using the techniques that we talked about yesterday. Okay, so that was about how to represent the solution. And remember that we do need a function that can quickly go from this solution representation to a travel time. So that's one of your challenges is if you're going to use an iterative algorithm, you have to write that function. So here's a drawing that we went through yesterday of a particular travel path. It starts at this depot, goes through a whole bunch of pickups and drop-offs, ends at another depot. And we can represent that, as I said a minute ago, in a vector. So we could say that is pickup 1, pickup 3, pickup 2, drop-off 1, and so on. So I'm just writing that all in a vector, and I don't bother writing the depots in because once again, my routine that just computes travel times can just pick closest depot on each end, and that's fine. There's no reason that I would ever consider starting this path from this depot, which is further away, which means I don't have to represent that option in the solution. It's just not a useful option. It's demonstrably inferior. Okay, so that's my delivery order. Now we said we want to be able to do perturbations, where permutations or changes to this delivery order and see if they're useful or not. That's how our iterative algorithm is going to work. So how would we represent changing the order of two deliveries? So we said maybe we could change the order of these two deliveries. We did that yesterday. And it was useful. Okay, so let's do that again. So we're going to change, that edge goes away. We reconnect it differently. This edge goes away. We reverse its direction, and our depots are wrong. So we have to fix up what, that we go to the depot after the last thing in our delivery path. So I just did that graphically, and I've got a valid delivery path again. But how do I do it in this solution representation? So what do you think? This is actually not a very hard question. So for what I just did, which is I changed the order of, instead of doing the second drop off as the last thing, I now do the second drop off as the second last thing, and the 0th drop off as the last thing. How would I change this delivery order to represent that? Because I can't. My computer program doesn't have graphics that encode its solution. I got to change this vector. Yeah. So Sarah's right. It's easy. Just swap the last two elements in the array. Okay. So if I swap those last two elements in the array, that's really fast, and I've now got a new solution. Now it's going to take me a little longer to estimate the travel time to see if it's better or worse. And again, that's one of your challenges, to figure out how can you do that quickly but accurately. Okay, so this one, the travel time was better, so I'm going to keep it. Okay, so a bit more complicated permutation operator is this two-opt that swaps and basically cuts up this path and reconnects it in different ways. Okay, so remember what we do for this is we first delete two edges. Okay, so, well, let's start with just writing down our delivery order again. We're going to delete two connections. Okay, so let me show that again. I'm going to delete this one and this one. That's my two-opt. Okay, so they're gone. So in my delivery representation, I'm representing that as just two bars. So I put two cut lines in to my delivery order. Okay, now I need to reconnect it. And I want to reconnect it differently. So let's say I reconnect it this way. I connect from one, pick up one to drop off one. I connect from pick up three to drop off three. So in order to do that, what I've actually done is basically reverse the order of this subpath. Okay, so reversing the order of this subpath is what it took to go from, the original tour or path that I showed you to this new one. Okay, so in general with two opts, you pick two edges in your delivery order and delete them. That divides your path up into three subpaths. So that's what I just did. With these vertical bars, I've picked where am I going to cut it up. I then can choose an order for these three subpaths. So I could swap them. I could try moving this subpath after this subpath. I can also reverse the order of any one of these subpaths. And some of these are going to be illegal, given that I have to do pickups before drop-offs. So I have to check if it's legal. So that's the procedure that you use to do two opts. Again, using this compact representation of the solution. Okay, so how many of those are there? Can we look at a significant fraction of these two opts or not? So if we have D deliveries to make, then we have 2D minus 1 edges or connections between delivery locations. So if we have 100 deliveries to make, we have 100 pickups, 100 drop-offs. That actually means there are 199 connections between these interesting intersections. Okay, so how many different two-ops does that lead to? So see if anybody knows that. If you know how many different ways could we, see if you can figure out how many different two-ops could we do. So I'll give you a minute to think about that. So the first thing I have to think about is how many different ways could you cut these edges? You're going to cut two edges, and there are 2D minus 1 of them. So how many different ways could you cut up this long path into three different subpaths? Okay, so I see 2D minus 1, C2. What is C? Choose 2. Yeah, okay. So TD minus 1, choose 2. And yeah, that's exactly right. Okay, so 2D minus 1, choose 2 is basically just 2D minus 1 times 2D minus 2. divided by 2. So let's say, put some numbers in. Let's say we got 100 deliveries to make. Then we'd have about 20,000 options. Okay, 199 times 198 divided by 2. So that's how many ways we can. Uh, so it's almost d squared, right? This is approximately d squared. That's how many ways we can cut up this long path into 3 sub pieces. Now we also can reconnect it in different ways. So there are 3 sub paths. We can choose to reorder those 3 sub paths, and the number of ways we can reorder 3 things is 6. So there's 6 different choices of order for that. And then we can choose whether or not to reverse each one of those subpaths or not. Okay, so that's actually 8 more options to reverse or not reverse each one of those. And if you multiply all this out, so that means 48 different ways we can reconnect things when we do a 2-opt with certain edges cut. In total, this means there are about 1,000,000 2-opts for 100 delivery pickups and drop-offs. That's not that many. Okay, that's not a small number. It's not going to be easy for a human to do that. But if your code is pretty fast, it can actually look up, use those techniques we talked about to look up travel times really quickly. You could try all of these. Okay. If you find an improvement, it means you've actually changed the path. And that means that some of the 2-ops that you did before, well, new 2-ops become available. Whenever you change the path, you could actually go back and say, okay, let's try all the 2-ops again, because they'll get different results. Our starting point is different. So you could iterate through this multiple times. So there are quite a few 2-ops, but not the number is still small enough that you could actually go and try them all, and you could do that repeatedly. Okay, so you can make other perturbation operators. 3-opt, basically a 2-opt again, takes a path and cuts it into 3 pieces. A 3-opt takes a travel path and cuts it into 4. Okay, so one of these pieces that I showed here would now be cut maybe into 2 pieces. So yeah, 3-opt cuts the path. You cut the path in 3 places, which means instead of cutting my long path into 3 pieces, I cut it into 4, and then I reconnect. So there's actually a lot more ways that you can cut something into 4 pieces and reconnect those 4 pieces. So there's a lot of choices for that. It takes longer to explore all those choices because there are many, many more of them now. So it's a judgment call. Is this a useful thing to do or not? It's going to provide more things to evaluate, but it's going to take more CPU time. Maybe you run out of time. Maybe some of these things are less likely to be good. So because they're bigger perturbations, maybe if you're running out of CPU time, you'd be better off focusing on some of the simpler perturbations. Another thing to think about is for the classic traveling salesman problem, which is just find a path that goes through a whole bunch of, in our case, intersections. 2-ops and 3-ops work very well. So some of the best solutions in the world use them. In our problem, we have this additional constraint of we have to do, if this is a pickup and this is a drop-off, we have to do this before we do this. Okay, so that means that a lot of our 2-ops, a lot of our perturbations could be illegal or will be illegal. So how do you deal with that? So maybe that means 2-ops don't work as well. That's one possibility. You might be able to recover some performance by making your perturbation operator prefer 2-ops that kind of cut out small pieces of the path, because it's more likely that reversing a small piece of the travel path is legal than reversing a really big piece. Maybe you can re-legalize it. So 2-ops are something that's used for classic traveling salesmen in the literature, but you can think about how could you adapt this. So if you tried changing this travel path, so you reverse the order of this sub piece, you said I'm going to cut this and I'm going to go through this in the opposite order. Clearly, it's illegal. But you could write code to say, well, why is it illegal? And maybe I can try to fix that in a way that's not too disruptive. Your basic illegality is that you're dropping off before you pick things up. So maybe you can fix that up with a smarter legalized perturbation operator. Maybe you make something different. So you're kind of inspired by these notions of just swapping 2 intersections or using things like 2-ops that can reorder entire parts of the path. But you come up with something a bit different that is either less likely or maybe not capable of making illegal paths, and therefore you can explore the space more efficiently. All those things are reasonable. So, okay. And yeah, I see someone saying k-opt. So yeah, this you can do for-opt and so on as well. So you can basically make perturbation operators that chop the path up into lots of pieces and try putting it back together. And now they can explore even more of the space. But there tends to be this trade-off of when you perturb things a lot, then well, the space of what you can explore is bigger. There are many more options, so you're less likely to get stuck where you just never try something. On the other hand, the space is really big, and most of those perturbations are quite disruptive, so they actually are a bad idea. So that's kind of your balance, right? If you're, yeah, more powerful perturbation operators let you explore more, but a lot of that exploration is going to be parts of changes that are too disruptive and turn out not to be a good idea. Okay, so any questions on that? If not, I'm going to go on to kind of giving an overview of how these heuristics fit together. Okay, so let's keep going then. Okay, so this is kind of just showing in a more abstract way how do these different classes of algorithms that we've talked about fit together. So what I'm drawing here is we've got a solution on the x-axis, and we've got the quality on the y-axis. So higher is worse because this is travel time. Um, and I'm showing this in one dimension, like that there, I just maybe am moving one thing. That's what my x-axis is showing. But really, we have a very high dimensional space. So if we have 100 deliveries to make, we actually have a 200 dimensional space that we're exploring. Of basically, for every one of those intersections of interest, where is it in our order? I can't visualize a 200 dimensional space, so I'm just visualizing a one dimensional one. But the real solution space is much, much more complicated. So these points where a small change is going to make the travel time go higher are called local minima. Okay, so these are all local minima because if I try to make a small change, it's going to make the travel time worse. And there can be, in general, there'll be lots of them in a problem like this. There's only one global minimum. So this global minimum is the smallest travel time that I can possibly get. Much harder to find because there's only one of it. And in general, this is a computationally hard problem, so we have no efficient method to go and find this global minimum and guarantee that we found it. You know, we might find it by accident, but even then, we won't know that it is actually the global minimum because we can't check everything. Okay, so how can we explore this? So we could just pick a random order. Um, you're given the deliveries in a certain order, you could just leave them in that order and just say, let's go find travel paths in between them and return that. It's probably going to be pretty bad. There are many more bad solutions than good solutions in this space. So if you pick randomly, yeah, your travel time is generally going to be a lot higher than the global minimum. We could do multi-start. So we could, instead of picking a random solution, we're going to pick a bunch of different random solutions. So we can make a program generate random numbers. That'll generate our delivery order, and we'll just pick whichever one has the best travel time. It's a little better. So I picked the best of these four random orders. It's a bit better, but it's still going to generally be pretty bad because on this plot, it kind of looks like it's almost as easy to find a good solution as it is to find a bad solution. But in the real 200 dimensional space, the good solutions are actually much more rare than the bad solutions. So picking randomly and then just taking the best of those picks is still not going to get a great answer. Okay, so what does a greedy algorithm do? A greedy algorithm is basically just making one decision at a time based on whether it's better or not. Okay, and it tends to get pretty far. It'll be a lot better than picking randomly, because it's made its decisions intelligently. It winds up in a better spot in the cost space. So it's a pretty reasonable algorithm. They're generally still not locally optimal. So there are small changes I could make to this that would make it better, but my greedy algorithm didn't know that because it didn't even know what the full solution was when it was creating it. Okay, so I can do iterative improvement. So I could start with that output of my greedy algorithm and I could start trying to improve it. And some of the things that I try, so here I make a small change and my travel time got worse. So I can reject that, say it's not a good idea, try a different perturbation. And that perturbation here was good. So I can say that's good, I'm going to keep that. And then I can try perturbing that solution again. And maybe I find that another perturbation makes things better still, and so on. Okay, so I can gradually make a bunch of different perturbations. I only keep the ones that are better, and I can eventually get to a local minimum. Okay, which is a lot better than when I started. And I can combine that with multi-start. So if I take a bunch of different, well, here I'm just running my greedy algorithm, my iterative improvement again. I find that local minimum. Still got CPU time left, so I perturb my greedy solution somehow, find a new starting point, run my iterative improvement, get to that point, and so on. So I do that in a bunch of different spots, a bunch of different starting points. So I'm somehow perturbing my greedy algorithm or starting algorithm, and then running my iterative improver on it. And I take the best of all these. So it would be that one. So combining these, I'm now combining three different algorithms: a greedy starting one, an iterative improver, and I'm doing multi-start. And they combine pretty well. So they can all work together well. Okay, local permutations can get stuck. Okay, so what do I mean by that? Let's say that I have a solution, greedy solution that puts me there, and I can make local perturbations to kind of follow down this downslope and get to here, which is pretty good. If I try from that point to make any small change, I can find, well, there's nothing I can do. Every small change I make is worse because I'm in the bottom of this bowl. But I can see that there is a better solution over here. It's not super far away. I don't have to make an enormous number of changes, but my perturbation operator can't get there. It's stuck. Okay, so that's where a more powerful perturbation operator could be useful. So maybe these small changes, that might be swapping two intersections, and it's just not enough to get me out of this local minimum. But if I have a more powerful perturbation operator, like maybe 2opt or some custom operator that I've created, basically I could, in one step, go all the way from this solution to that solution. And it basically just jumps right over this bad spot, and I can see this is a better solution. And once I get to that better solution, smaller perturbations, a variety of perturbations can let me follow this travel time or cost down, and I can find this better solution still. Okay, so more powerful perturbation operators are less prone to getting stuck, but again, because there are many more large-scale perturbations, you can also run out of CPU time. If you can only explore a very small fraction of those perturbations, maybe you just waste your time, right? Maybe you waste your time just checking out here and way far away, and you would never find anything useful if your perturbation operator was too disruptive. So there's a balance there. Yeah, and Trevor's saying that there are some things you could do here, like maybe it has a small chance to try a really drastic change. So that's a reasonable thing to do too, right? You could try a lot of like local changes, and once in a while try a really big one, or try local changes as long as they're getting gains. And if it seems like they're no longer getting gains, try a bigger change. At a certain point, if the change is big enough, it's kind of like just restarting your algorithm, like multi-start. So there's some overlap between these concepts. And Isidore has a good point as well of it often makes sense to make drastic changes earlier on. So early on, when you start your solution, you've got an initial solution somehow, maybe with a greedy algorithm, you don't know if it's very good. So a lot of perturbations you might want to explore the space in a lot of different ways. So make pretty big changes so that you kind of bounce around a lot and hopefully you get somewhere like there. Once your solution's been pretty refined, you might make smaller changes, trying to just refine it and maybe find all the way down to here. So those are all good ideas. There's a lot of craftsmanship and cleverness in trying to create an algorithm that works well for a hard problem like this. Okay, and I basically just said all of those things. Last thing is hill climbing. And I see this has been actually mentioned by Eric. He mentioned something called simulated kneeling, which I'm going to talk about in a second. And simulated annealing is a technique for hill climbing. It's not the only one. So, what hill climbing means is so far when we've talked about perturbations, we've always said you evaluate, does your change improve travel time or not? And if a change doesn't improve travel time, you reject it. You don't make it. Okay, so in that case, we would never, we would just reject this red solution. It's worse than the yellow one. We'd throw it away, go back to the yellow one, keep trying to change it. With hill climbing, there's some chance that we're going to keep that solution, even though it's inferior. Okay, now why would we do that? The idea is that we're climbing a hill in the cost space. Things are getting worse, but maybe after a while they'll get better again. Okay, so here I did another hill climbing change. I perturbed the solution, the travel time got even worse, but I haven't given up yet. And now I try another perturbation, it actually gets better, and more and more and more, and actually all of these get better. So it turns out that the first couple of perturbations looked bad, but I kept trying anyway. And eventually I started finding perturbations that reduced my travel time more, and I got to a final solution which is better than my initial solution. So it can also help me get unstuck from local minima. You have to be careful with it because you could obviously burn a lot of CPU time perturbing things, to worse solutions. And, you might just keep perturbing until you get way up here. And now you might have burnt a lot of CPU time and gotten to a pretty bad spot. And hopefully you remembered that you had a better solution so you can go back to it, but you still wasted a lot of time. So there's a balance here too. Too much hill climbing can just make you waste lots of time. Okay. Yeah, and if you do hill climbing, you don't want to run out of time right when you're hill climbing. The whole purpose of hill climbing is to get you to some spot where your later improvements make it better. So you need to have enough CPU time to do that. Otherwise, you're better off not doing any hill climbing. Okay, so yeah, hill climbing is a way to get out of a rut. So you change something, even if it looks like a bad idea at first. So sometimes your algorithm can tell all the perturbations that I'm making they're not helpful. So I'm going to save my solution because it's pretty good, and then I'm just going to make some perturbations that initially are not helpful to see if I can get to a better place. So how can we do that in this problem? We could change our delivery order. Okay, even though it increases travel time, and it's a good idea to save our best solution before we do that in case we don't get back to a better solution after some amount of effort. We'd like to go back to it. So this is, I guess, an analogy to this is kind of like you're a bit unhappy in a relationship. Things aren't terrible, but you think maybe there could be something better out there. So the hill climbing move is breaking up with your current partner and going off and dating, seeing is there something else that could make you happier, um, and maybe that doesn't work out. Now, what you can do, so that's the same idea of what we're doing in an algorithm here. What we can do in an algorithm is hard to do in that romantic analogy, though, is that you can save the current solution. You can try your new hill climbing move, exploring some other changes. And if they don't work out after a while, you can basically eventually go back to your saved solution. So I recommend you save it. Um, this is hard to do in a relationship because it's hard to break up with your boyfriend or girlfriend and also say, but I'd like to try a bunch of dating, and if it doesn't work out after 3 months, we'll just get back together. But you can do that in computer code, so it's a good idea. Okay, so that's the idea of hill climbing in general. Uh, let's talk about a specific approach for hill climbing. So simulated annealing is sometimes called a meta heuristic. So a meta heuristic means it's like a broad idea that you can apply to a lot of problems, kind of like greedy algorithms or iterative algorithms. These are all really broad ideas. Okay, so simulated annealing comes from analogy to annealing metals. If you want to make a strong alloy, you actually want to cool the metal kind of at the right rate. You cool it relatively slowly, and the idea is that that means the atoms in the alloy have time to move to a low energy state, which makes your metal stronger. Simulated annealing is basically an optimization framework that mimics this process in a computer program. What it does is it starts with so the solution is essentially analogous to the arrangement of atoms in the metal. And in your program, you have a parameter called temperature, which behaves exactly like the physical temperature. So we start with a poor initial solution. Um, our delivery order is not very good. It means we're in a high energy or high cost state, high travel time. And we set the temperature to be pretty high. And now we're going to perturb things. So that's like atoms randomly moving around in the metal. When the temperature is high, things can move easily. So most of our perturbations are accepted, meaning that the atoms move, the delivery orders change. But we gradually reduce the temperature. And as the temperature drops, um, it gets harder and harder for your delivery orders to change or your atoms to move around in metal. So as the temperature drops, only good perturbations are accepted. So when the temperature approaches zero, which is called quenching, in metal, in annealing, that means you basically stick the metal in a bunch of water and it cools off really fast. When the temperature is zero or is very close to zero, basically only perturbations that reduce your travel time would be accepted. But early on, when the temperature is high, you'd actually accept a lot of perturbations because you're trying to explore the state. And in annealing metals, this works better. You get a stronger metal by slowly cooling the temperature, cooling the metal, than you do by just taking a red hot bar of metal and sticking it in water, because you're giving the atoms time to find a low energy state. And it's exactly the same thing you can do in a computer program. Okay, so that's the analogy. What does this look like in pseudocode? Basically, we have something S. S represents the solution state. So that would be that delivery order vector that I showed you earlier. And so we make an initial solution somehow. It could be random. So it might just be the order you were given the deliveries in. It might be you choose a random order, or it could be smarter. We might run a greedy algorithm, for example, to get an initial solution. There's some cost. And for us, what do you think the cost is? So this is a test to see if people are following me at all. In our problem, what do you think the cost would be? Yeah, so the cost is the total travel time for us. And then we need to set a temperature. And we want it to be high initially so that we actually can do some hill climbing. We have a chance of accepting perturbations that are not good, but there's still a question of how high. And it actually depends a bit on what is our initial solution. If our initial solution was really bad, if it was random, so random S, you run a pretty high T, meaning that, like basically all perturbations are accepted. You don't want to set it to be infinity, because that's kind of like an infinitely hot metal. It's going to take a really long time to cool down, but you want to set it high enough that pretty much any perturbation is accepted. If your initial solution is better than that, so if say it's a greedy S, which means it's probably pretty good, then you kind of want a medium temperature. You don't actually want to accept all perturbations, because that's kind of like melting your metal bar down. Like you're just going to destroy your greedy solution. This is actually a little more tricky to figure out, what does that mean. So you want to accept some hill climbing, but not too much. So maybe small degradations are okay. Really big degradations you would like to be unlikely to be accepted, because they'll destroy your greedy solution. Not There's a lot of craftsmanship to making this algorithm work. So there's no one answer of what is the best to do amongst those things. Okay, so then what does the main loop of simulated annealing do? Basically, as long as the solution is still changing, you're still getting gains, or you still have CPU time, because you might run out of CPU time, but you keep going through this loop. So your loop is you perturb your solution, so you permute it somehow, and that gives you a new state, so a new travel order, or a new delivery order. You compute the cost of that new delivery order, so the new travel time. And again, if you can make some fast code using all the techniques we talked about earlier, that's going to let you evaluate a lot more perturbations, which is good. So we get the travel time, or the cost of this perturbation, and we compute the difference. Okay, so if the new travel time is lower than the old one, then we get a negative delta C, which is good. If the new travel time is higher, we get a positive delta C, which is bad. Okay, if the new delta C, the new cost or travel time is smaller, then we for sure update our solution. So we say our delivery order is that new perturbation, and our travel time is that new travel time. So far, this is basically the same as iterative improvement, right? If I just call all this iterative improvement, this is what you're doing for it too. What annealing does is, and then we reduce the temperature. Okay. What annealing does is it adds in an or. Okay. So you basically choose a random number. So there is a function called random. Um, Actually, I have to go look. But basically, there are lots of random number functions in C++. There's one called rand. There are lots of other ones. So you ask for a random number between 0 and 1. And then you check, is that number less than e to the negative delta c over t? Okay, now what does that mean? So if the change in cost was, let's say, negative delta c is 3 seconds. So that means that the travel time got 3 seconds worse. Okay, so if negative delta c equals 3 seconds, that means 3 second degradation in travel time. If my temperature, if t equals 0.1, the probability of accepting this is basically e to the negative 30. I need to get a number that is between 0 and 1 that is smaller than e to the negative 30. The probability of that is not high at all. So very little chance that it'll accept that. But if t was equal to 10, then I need to get a number that is less than e to the negative 0.3. And e to the negative 0.3 is almost 1. Okay, so the probability of that is pretty high. So basically, when t is big, even large degradations in cost or travel time are pretty likely to be accepted. When t is small, then they're very unlikely to be accepted. And eventually, if t equals 0, then you will never accept anything for this reason. It will only be things that improve it. For this algorithm to converge to a good solution, we need to be gradually reducing the temperature. Okay, and this is also tricky. So how fast do we reduce that temperature? Um, what are these perturbations? It might be smart to make smaller perturbations as the temperature drops, because we know that big disruptions or big hill climbing moves are not that likely to be accepted. So there's a lot of tuning, a lot of cleverness that goes into an algorithm like this. Okay, and I already said that. How quickly do we reduce temperature? Um, I haven't shown this in the pseudocode, but usually what you would actually do is you'd probably wrap a loop, for I equals 0 to 1,000 or something. Um, you might basically do a lot of doing one perturbation at every temperature is a bit unusual. So you'd probably do a whole lot of perturbations, 1,000, 10,000, some number before you try to reduce the temperature. Or you would reduce the temperature by a very small amount. It basically would work the same. But if you're only going to do one perturbation at a temperature, then you better reduce the temperature by a very, very small amount, because the idea of annealing is you will try a lot of perturbations. Hopefully, you make your code very fast and you can look at millions of perturbations, because that's where some of the power comes in. If you can only look at 300 perturbations, this is not a good idea, right? You're going to waste too much time with this hill climbing. You just shouldn't do it. If you can look at millions, this starts becoming more interesting. Okay. Um, the last thing I'll say about this is sometimes people go, well, just like M3. In M3, the last algorithm I showed you was A star, and that was actually the best algorithm. That is not true for Milestone 4. For Milestone 4, I'm showing you 4 classes of kind of broad algorithms, and each of them you can put a lot of cleverness into it. And this simulated annealing, which incorporates hill climbing, is kind of the most tricky one to tune. And it can benefit from the other algorithms because you can give it a better initial solution. You can give it smarter perturbations. Do not say this is the last algorithm, so I'll code it first. Code the simpler ones first. They're important building blocks if you do something like simulated annealing. And simulated annealing properly done can be quite powerful if these building blocks are good, but it is also quite tricky to tune, and it doesn't work well if these building blocks don't work well. So I don't just jump to this right away. And you may never want to do it. I've had one student in the prior year who basically made a greedy algorithm work very well, and repeatedly posted that the third and fourth algorithms are totally unnecessary. Greedy is all you need, and that was true for him. He made a good greedy algorithm. So again, don't interpret this as because I went through it in a certain order that you have to go to number 4. Okay, so we talked about algorithms for milestone 3 and 4. And that's it for how much I'm going to talk about algorithms in this course. But if you want to learn more about optimal algorithms, so you got a perfect solution, you can do proofs, etc. So things like M3, where we did Dijkstra and A star, take EC 345, algorithms and data structures. It's all about proofs, complexity analysis, no coding. How do we come up with provably good algorithms for various problems? What I've been talking about in milestone 4 incorporates heuristic algorithms for which we use for computationally hard problems. We don't really have an undergrad course on that at U of T because it's getting more advanced. But there are a couple of grad courses that, if you want to take a grad course in 4th year, you could explore. So this one is basically computationally hard problems that come up in the automatic design, the computer design of digital circuits. There are a whole bunch of them, and this talks about how you attack them. And this course, 1724, is the same idea, computationally hard problems, but they're ones that come up in essentially cities. Okay, so algorithms to optimize traffic and city design, and they actually use OSM data. So you'd actually know a bunch about what they're doing there. Some of the algorithms that you use here, we just talked about simulated annealing. That's one of them. Another broad class is called genetic algorithms. So if those kind of interest you, those are courses that go into them. Okay, any questions about any of that? Why is the class code so high? This means grad course. When you get 4-digit codes, it means a graduate. So you probably won't take these courses, but every year there are in grad courses at U of T, undergrads are allowed to take them. So some undergrads will take a grad course or two in their 4th year. Grad courses are more work, so I wouldn't recommend taking a whole pile of them. But if these kind of interest you, you could take 1 or 2 in 4th year. Okay. I want to talk quickly about managing the time limit. So milestone 4, we give you 50 seconds to solve each problem, and whether it's big or small. You can get better results by using more CPU time. So you can in different ways. So we could run. You've written a certain algorithm. If you can add some randomness into it, you can run it multiple times with a new starting point and get a better answer. And there's not much code to do that. So you can turn CPU into result quality. Iterative improvement, you can just keep proposing more and more iteration, more and more perturbations and seeing if you find something good. So you got a couple ways that you can improve your result if you just keep working at it. But we got a 50-second limit to return your solution. And you want to make sure you return the solution in less than 50 seconds or the unit test will time out and say that's no solution. It's going to be hard to code, just try 10 starts or try 1,000 different starting points, because we're going to give you different numbers of deliveries. We're going to run in cities that have different sizes. So it's difficult to just say, well, I can always run my algorithm 10 times. Maybe sometimes that's way under 50 seconds and maybe times that's over. So what we can do instead is we want to actually check how much time has passed and end optimization just before the time limit, if you're basically leveraging these techniques to get as much as you can. Okay, and the way to do that, we already talked about earlier in the course. You can use the chrono library that's in C++. Now I'll just give you the sample code. So your time limit is 50 seconds, so defined a constant. I shouldn't use magic numbers in my code or I'll use lose style marks. For M4, we're not grading your style, but you should still always use good style. Okay, so in my main program, I can basically say, tell me what time it is right now. And I'm going to say that I'm not out of time. And as long as I still have time, I'm going to call some optimizer. And then I want to check, okay, what time is it now? I know my starting time over here, and I can now get what is the current time by just calling this now function again. And I can basically, sorry, there's too much animation, but with a little bit of chrono code, I can basically say, okay, turn that into the time difference. Okay, so that tells me how much time have I used so far. And to get that time in seconds, I write this wallclock.count. So it converts from the chrono object to a time in seconds. And I'm going to leave myself 10% guard band. So I'm going to say I'll use 90% of my time limit to optimize. Once I hit that, I say the timeout is true. I'm going to break out of this while loop, and maybe I have some final computation to do to return my solution. So you want to leave a little guard band here. Don't go all the way up to 50 seconds. Okay. Um, and let's see, those are all the code I've given you. There are multiple definitions of time in a computer. The code I've given you is the like actual elapsed time. Like this matches what you would measure on a stopwatch, no matter how many CPUs you're using. So you can also ask a program to tell you how much CPU time you've taken, where it basically adds up how long you've been running on all the CPUs you've used. You don't want that. You want how much stopwatch time have I taken, and that's what this code will do. Okay, so we're going to talk next week about another technique you can use to stretch this time budget, which is that the processors that you're using in the undergrad lab actually have 4 cores in them. So you can actually run 4 threads if you wish. You don't have to do this. So we'll talk about how to do that at the start of lecture on Wednesday and in the tutorial next week. So you can stretch your time budget by doing 4 times as much work if you want. It's also a useful programming technique to know. So basically, we also just want to introduce you to it. But again, you don't have to multi-thread. So it's not something you should try doing until you have a good solution going, and you shouldn't do it unless you just feel the need for a challenge. How are we going to grade M4? So M4 is completely graded by the auto tester and me looking at the results. So whenever you submit your code, you will go into a leaderboard. And this is actually showing a leaderboard from a couple of years ago. So we're going to, we don't have the leaderboard going yet, but one of the head TAs and myself are working on it now. So it should be up this weekend. We're going to insert a few reference solutions in the leaderboard. Okay, so TA good is us trying really hard. We wrote the best solution that we had time to. So we're, myself and the head TA are busy. So we kind of give up after a while, but it's a pretty good solution. We also wrote a relatively easy solution to code using some of the simpler algorithms we talked about at the start, but it's decent, right? We put some thought into it, but it's not that much code. We call that TA moderate, and then we have TA bad. And TA bad is basically we don't really optimize the delivery order at all, right? We just take a random delivery order and route it, which is connect it. So you can basically predict your grade by looking at where you stand compared to these. If you get at equal TA good, and what this is showing is basically how many tests did you fail? So you don't want to fail any tests. And what is your average quality of results? Okay, so your average quality of result is your average travel time. And the travel times can be pretty big because some of these problems are pretty big. And then we show you how different are you from the best solution. So the best solution's up here, and the TA good was 27% worse. If you equal or better, well, if you equal TA good, you'll get 90%. If you do better, then you're above 90%. This one is worth 70%. Okay. And it's a lot easier to get to that point. The algorithms are simpler. And the random delivery order, so not very good, but did manage to complete all the problems, is about 30%. We'll also have some corner cases. So when we write in the header file, if the following happens, return this value, we are going to test that. Okay, so read the header file. If you don't read the header file, you're going to fail those corner cases. There aren't a lot of them, but we write them down. So read the header file, handle those properly. Otherwise, it'll be about a 10% penalty. If you're above the TA good, then you're above 90%, and the top 4 teams will get bonus marks. 4% total course mark, so not 4% on this assignment, 4% on your overall mark for the top team, and then 3%, 2%, 1%. So it's not competitive except for the teams that would like to be amongst these top 4. For everybody else, we fit a curve that goes through these 3 points. So if you're partway in between these two, you'll get a grade in between them, and your grade's computed from that. Okay. Let's see. What percent of students beat TA good typically? It varies year to year. Last year, quite a few students did it. Maybe it was about 15% of the class got above TA good. Okay. What performance is required to get 100% of the base mark? That's a good question. It's a little better than TA good, not that much. So we kind of fit a curve through there. And let's see. Definitely these two would be up at 100% in the bonus marks. These teams would be somewhere in the 95 to maybe 100% range. Okay, so When I say competitive, so someone's asking, what about, isn't it competitive to get between, these 2 points? You're not competing against each other. Okay, so sometimes students get worried. Well, am I competing against Bob, who's down the street from me? Should I try to sabotage Bob? No, you're not competing against Bob. Yes, you are trying to get if you're at TA moderate and you get closer to TA good, then your grade will also become closer to TA good. So we don't just bin them. We don't say, you're either 90 or you're 70 or 30. We fit a smooth curve through all these. So if you're just a tiny bit worse than TA good, then you're going to get a tiny bit less than 90%. Does that make sense? Um, and we'll definitely give you marks this high. Uh, if the whole class did badly and nobody was getting up to these levels, which is unlikely, then we'd probably make it even a looser grading scheme. But that's never happened, so I'm pretty confident that a bunch of people will beat TA good and we'll stick with these numbers. But no matter how many people get above TA moderate and TA good, we'll give you at least a grade this high. Let's see. If our code is deterministic, will your leaderboard scores stay the same between multiple tests? No, the tests themselves don't have randomness. So if you run the test over and over again with the same code, you will get the same answer. This leaderboard will only update when you submit. You can go compute it yourself after exercise if you want. And it's anonymized. So we will basically send you can see this in the Milestone 4 handout. You will be sent what is your anonymous ID. So you know who you are on the leaderboard. No one else knows who you are. So they know there's somebody with this score. They don't know who that person is. Okay. And yeah, you will see TA good and TA moderate and TA bad on the leaderboard. So it literally looks like this. We actually, basically myself and two of the head TAs will submit solutions, and we basically make it appear that these are our anonymous IDs. So you'll see them show up right in the leaderboard. And we'll get them in there and then we'll leave them. Okay. So we're not going to keep working on them. It's possible for the first day we'll just say, oh, we had a bug. But once we have them in place, we just leave them alone. We don't keep trying to make them better. And the leaderboard shows your most recent result. So every time you send something in, it takes the best result from your team. Okay, so if all 3 team members submit and it's 3 different solutions, it will show the best result of the 3 of you. If all 3 of you then submit an inferior solution, it will then show you your new score, which is lower than your old score. Okay. I don't think we'll have any bug. Like once we get these in, I'll take a look at them and make sure that they look right. So after this weekend or early next week, these TA good, moderate, and bad should all be quite stable. But the leaderboard's not up yet. So all of the tests for M4 are there. You can start writing. You can start optimizing. You won't be able to see your score on the leaderboard yet. Okay, so if there are no more questions, I'm going to end the lecture. I guess I'll hang around for any additional questions.
Oh, sorry, could I just ask you one thing?
Sure. I'm just going to